So, welcome to this the second video in a series of videos on the topic of tuning the data warehouse. My name is Joachim Snygg, and this video is part of the course IS5 Data Warehousing that is given here at Stockholm University. So, relational database indexes. I'm sure most of you are already familiar with that topic. An index is serves the very same purpose in a relational database as it does in a book, for instance. If you want to read about a certain topic in a book, instead of reading the whole book until you find the topic that you're interested in, you can go to the index and scan through the index, find the topic, and then you will have a reference to a certain page. You will have a page ID or a page indicator that indicates which page you can find that information on. In a relational database, it's very similar. You will have a list of values from an attribute. That would be the list of topics. So you choose an attribute, and then all the different values in that attribute have references, have pointers to certain row IDs, or RIDs as we call them. So instead of scanning the whole table, you can just go to the index and find the topic that you're interested in, for instance pink tissues, and then you can see that, okay, I can find pink tissues in row ID 5, row ID 10, and row ID 216, for instance. So in this video we're going to talk about a few indexing techniques that can be used in data warehouses. So we will talk about B+3 indexes, bitmap indexes, join indexes, star join indexes, and bitmap join indexes techniques. But there's a lot of other indexing techniques. We have projection indexes, hash indexes, spatial indexes, and so forth. But we will focus on these as these four that you see here in the indexing technique section, because those techniques are beneficial when we're talking about data warehouses. So they are not specific to data warehousing. These indexing techniques you will use in all relational databases, or you can use them in all relational databases. But those indexing techniques is very useful when we create the physical design of a data warehouse and optimize it. Then we will probably make use of some of those indexing techniques, depending on the database management system that we use. So, when are indexes used? Well, we use indexes when only a small portion of the tuples are read. So if we look at the book example, if we still are going to read the entire book, why then read the index as well? It will just be more reading, rather boring reading for that matter. So then we will just read the full book. If we are going to make a full table scan, we don't need to go to the index as well. It will just take more time. So we only use the index when we only need a small portion of the tuples, when we only need a small portion of the pages in a book, a small portion of the tuples in a relation, a small portion of rows in a database. In data warehouses, often all tuples are read, and then indexes are of no use, as it will be more to read. In the ETL process, deals with extracting data from the sources, source databases and flat files and so forth, transform that data and then load it into the data warehouse. But when we load it into the data warehouse, it's very possible that we need to check that the data that are coming in, that we don't already have it in the data warehouse. For instance, if we have a record of a certain sale, then we must check that we don't already have recorded that sale. Otherwise, we would store the sale twice, and that would lead to heterogeneous data and heterogeneous analysis. So in ETL, we do a lot of lookups. We check when we get incoming data, Is this new data? Should we just disregard it? Should we update some old data? Should we insert a new row? What should we do? And then we use a lot of lookups, and then instead of doing all these full table scans of our rather huge dimension tables, we will rather look at indexes, just at the index that we need, because indexes are as you see, much faster. And then predicates in OLAP. So predicates are usually found in where clauses. So it's operations like compare or greater than and so forth. And this eats up performance. So to avoid, you can use indexes to avoid using predicates in OLAP. And then instead of using a predicate in the tables, you can just go to an index instead. And we will see examples of that in join indexes specifically. So let's start with a basic indexing technique called B+tree indexes. It's based on B trees from Bayer and McWright in 1972. So this is from the early days of database methodology. I think Cod came up with the concept in like 1970. So this is at the time when we started to focus and research and think about digital data storage. So in B trees, each node has two branches. So if you look at a node, you can go either one way or the other way. A B+ tree basically is not binary, but you can use more branches. So you can say you can either go that way, that way, that way, or that way, or that way. So you have more choices in the more branches in the tree. So, for instance, primary indexing, where we store the primary keys, where each leaf points to a single tuple, that's when we use B+ tree indexes. So for instance, when we said that each row needs to be unique, we actually store that as an index. And that index creates the primary key and we say that each row with this primary key, with these attributes, need to be unique. So you can use in OLTP, you often use indexes you must use indexes to have unique rows. But you also have secondary indexes, and they are built on any other of the relational attributes. So, for instance, in your database methodology course, I'm sure that you, in one time or another, introduced a surrogate key. And then you said that if you have, for instance, a surrogate key for rooms, and you have a room number as well, then you still need to make sure that the room number is unique. For instance, in a hotel, you can't have two rooms with the same room number. So then you would have a primary key that is something else, and then you would say that, well, room number also needs to be unique, and then you would create a secondary index and say that that secondary index, each instance must be unique. So we create unique identifiers with the help of indexes, and we can also pre-sort searches. We can create an index and sort that index in another way. So for instance, in a book, you can have an alphabetical index, but you can also have other types of indexes of what matters most, or in a database you can have other attributes that you sort on. If you have car models and car manufacturers, perhaps car models is the primary key, and then car manufacturers can be another way of just sorting the data. B+tree indexes are used in high cardinality attributes such as unique row identifiers. The definition, I'm not sure that this definition really helps so much, because it's kind of easy to understand and the definition is kind of hard to understand. But anyway, a B+tree index on an attribute C, think of C as a column, of a relation R, well, that is a table. So we have the attribute, the column of the relation R, is a balanced tree providing associative access to the tuples of that table, of that R, on the basis of the values of the column key. So that's what we said, that the uniqueness from the column, right? So we sort it by the attributes in the column, the values in the column. The leaves of this tree are linked to each other and store the pointers to the disk blocks containing tuples. And we talked about disk blocks in the first video on physical design. Internal nodes create a map used to find key values quickly. So here is an example that makes it much more simpler, I think, at least. So let's say that we're looking for the value 28. Then we look at the first node and we go to 18. Well, 28 is less than 18, so let's just move on, and then we see 35. Well, that's more. So then this section is where we is for us. So in this section we have a pointer to this node, and here we start from the beginning and say 25. No, 28 is more than 25. And then we have 34. 28 is less than 34. So then it's this section that we look upon and follow. And then here we have a pointer to this node, and this node we start with 26. No, 28 is much more than 26. 27, no, too small. 28, there we are. And then we have a pointer in 28 that directs us to the data page, the block where we can find the data block, where we can find the information on from that row. So in row 28 we can find, for instance, information on pink tissues and what other attributes pink tissues might have. Another indexing technique very commonly used in data warehousing is called bitmap indexing. So bitmap indexing came from the late 80s. It was invented by O'Neill, and this is used in low cardinality attributes in opposite to B plus tree indexes. So the B plus tree indexes, if you think for instance of a primary key, then you have a very high cardinality of the attributes values, because each value needs to be unique. So it will have a new value for each attribute. So that means that you have a high cardinality of the attributes. In bitmap indexing, we look at low cardinality attributes. So attributes that we have a very distinct set of values to choose from. For instance, if you're familiar with UML class diagrams, we have a pattern, a model pattern called power types. In power types, we use power types to lift out all attributes that refers to, for instance, categories or types or roles, and we say this is a very limited range of values those attribute can take, so we lift them out to a power type class. Those decisions, when you decide to lift it out as a power type class, that is the same place where you choose to have a bitmap index, because you have a low variety, a low cardinality of the values in the attributes. So each value in the index column corresponds to a structure with a bit and a formula for a row, a read, a pointer to a certain row ID. So we use this instead of a full table scan. They can contain null values, which might be interesting, but we're not going to address it here. So the definition: a bitmap index on an attribute C, on a column, of a relation R consists of a bit matrix B. A bit matrix B is the table with the index. And this table, the bit matrix table, has as many columns as the distinct values of the column C, and as many rows as the tuple in the table of there are relation. And this means that the B is set to 1 if the column attribute value of that tuple, for instance, third tuple. So an example of a very low cardinality attribute would be man and female, male or female. There we would have two values. So if we say, for instance, that male equals 0 and female, that's not. So if we say if we have a male, then we would say that that's 1, and if it's not a male, then it would be 0. And if we have a female, then that would be 1, and if we don't have a female, that would be 0. And that also opens up for people that don't have any of the attributes. So here in a gender index, we can see that we have 7 rows. And then when we look at it, we can see that the first row with read 1, there we have a male and not a female. And row number 2, then we have a female, not a male. So we store 1 bit there and 1 bit there. Row number 3, then we don't know either if it's either a male or a female. The same in row number 4. So so you have to think about when this might apply, when this table might be used. I can't come up with an example myself, but I'm sure there's a perfectly good example where we might have people that we don't know if they are either male or female. And so, I mean, we're a little bit of both, all of us, aren't we? And then we have row ID 5, then we'll talk about a female. Row number 6 and row number 7, we don't know what we talk about. All we know is it's not a male or a female, I guess. So the example, the attribute sex has value M and F. A table of 100 million people needs 2 lists of 100 million bits. And if you think of a character, then you would store a byte at 8 bits. So if you need to capture if someone is either male or female in a table, and then you have other attributes, and you have 100 million of rows, then that table would be huge, right? But the bitmap index wouldn't be that huge. It would be like, it wouldn't even be a gigabyte. It would be very small. And then we talk about bitmap indexes. And they have tree structures similar to B trees to speed up searches, but the leaves contains bit vectors instead of reads. So here we have for row ID, we have the bit vector 1, 0. And for row ID 2, we have the bit vector 0, 1. And for row ID 3, we have the bit vector 0, 0. So steps in bitmap searches. How does the database management system deal with bitmap searches? First, descending trees, then you load the tree, then you're singling out the reads related to the bits set to 1, and then you retrieve the specific tuples from the table. Yes. So here we have an example of a base table containing customers, and then we have regions, ratings, and then as we can see here we have other attributes as well. And then we have the region index and we have the rating index. And then we also have a SQL question where we say select customers from base table where region equals W and rating equals L. So this example is from Ramakrishnan and Girk. So consider that we have this table, and the customer, I guess, is integer, and then we have region string, we have rating string, and then the domain region. The domain that we have in this attribute is N, W, S, and E. That means that we have north, west, south, and east. That's the four different values that are accepted. So that's the domain of that relation. And then we have in the domain rating, we have H, M, and L. And H, well, that means high rating, M means medium rating, and L means low rating. So columns with few possible values are sometimes called sparse, like region and rating in this example. And we can exploit sparsity to construct a new kind of index that greatly speeds up queries on these columns. The idea is to record values for sparse columns as a sequence of bits, one for each possible value. So for example, a rating value is 100 or 010 or 001, as 1 in first position denotes high, 1 in second position denotes medium, and 1 in third position denotes low. Similarly, for region we can look at the same thing. There we will have 1000, which would denote north. We would have 0100, that would denote south, as in this example. We would have 0010, that would denote east. We don't have an example of that. And then we would have 0001, that would denote west, like in row ID 3. If we consider the rating value for all rows in the customer table, we can treat this as a collection of a 3-bit vector. One of which has the associated value high, the other one that is associated value medium, and the third one that has associated value low. Each bit vector has 1 bit per row in the customer table, indicating whether the value in that row is the value associated with the bit vector. And the collection of bit vectors for a column is called a bitmap index for that column. So, if we look at this example, we can see that bitmap indexes offer two important advantages over conventional hash or tree indexes. First, they allow the use of efficient bit operators to answer queries. For example, consider the query, how many customers from the West region are rated as low? We can take the 4th bit vector for region and do a bitwise and an AND, like here, with a 3rd bit vector for rating to obtain a bit vector that has 1 for every West living customer with rating low, and we can then count the number of 1s in the bit vector to answer the query. Second, bitmap indexes can be much more compact than a traditional B+3 indexes. And they are also very amenable for the use of compression techniques. In video 1 we talked about how you could make searches more efficient by using compression. So think of a bitmap index where you, instead of searching strings, you search bits, and those bits and those tables are compressed as well. So then you will have very, very efficient searches. So if we look at this question, we can see region W. Well, that would, in this base table, that would mean that we will have row ID 3, 4, 6, and 7. They are west. And then we have the rating L. Then we would see that rating L, low rating, that is row ID 3, row ID 5, and row ID 6. So now all we have to do is use the AND operator. And then we will see that row ID 3 is west and low, and the row ID 6 is west and low. So those are the two rows that we need to look at, and then we can take the row IDs 3 and 6 and go to the base table and extract more information from there. So bitmap indexing is very useful when you have Boolean operators, and or not. So for instance, if you would say I want to look at region west, but that doesn't have a low rating, then you would say region V and not rating L. Or if you would say, I would look at rating West or things with rating low. So then bitmap indexing is very, very useful and very efficient. In bitmap indexing, you can sometimes solve queries without actually accessing any data through a table scan. So for instance, if you want to count all rows that have region West and rating L, then you wouldn't even have to look in the table. You would just have this bitmap vector to search through these compressed bitmap vectors. It would be so efficient. Zoom. Okay, so accessing data, touching rows, and performance issue. Yeah. So here we have a figure showing that the usefulness of bitmap indexing actually is a function. So the number of leaves requiring to store a bitmap is shown on this axis, and the unique rows, the natural keys in the table is shown on this axis. And then you can see that the higher value of unique identifiers. So you will see this function very clearly. So what you will see is that bitmap indexes are more suitable for indexing attributes with a reduced number of distinct key values. Right. And then we have join indexes. Join indexes, Valduris 1987, so it's also from the late 80s. Pre-process and explicitly store row IDs of matching tuples in two relations. Traditional indexes, as we all know, they map the values of one relation, of one table. And the idea with join indexes is that those indexes can span multiple relations. So the definition is that a join index between two relations, so the first table is called R1 and the second is R2. They store couples of tuple row IDs that fulfill the column 1 operator column 2. For instance, that the column in the first table equals the value of a column in the second table, like in a join, right? So then you would say that the predicate between the two attributes C1 is an element of the table R, and the column C2 is an element of the table R2. So what it basically means is that instead of joining two tables, you can go to an index and just see which rows are connected to each other in two tables. So that's a join index. A star join index is especially useful when we make our star join schematas, because when we have a star join schemata, then we will have one fact table, then we'll have several dimensions around it, right? So a star join index is doing the same thing as a join index, but with more than just two tables. So it joins, it provides an index for which fact tables rows are connected with all of the dimensions. So this is an example. We have a sales fact with the foreign keys from location, the foreign key from product, and the foreign key from date, and those together is the primary key, right? So then in a star join index here we can combine the rows. So here we have the sales on a certain locality, a certain product, and a certain date, and here's the quantity. And here we can see the different locations: Stockholm, London, and Paris. We can see the products: Channel 5, Noah, Opium. So we are dealing with perfumes here. And then we have dates. So this seems to be actually not dates but rather on month, so this would be a month aggregate, I would assume. Aggregates we'll talk more about in the next video. And here we have the index, where we see that row ID 4 that deals with Stockholm, channel 5 and date 1st of January, or January, I guess it is. So bitmap joined indexes is a way of combining join indexing and bitmap indexing. This is from O'Neill and Grief, and they are used to avoid joins between dimensions and facts. So bitmap join indexes is usually used in data warehouses. They define columns from the dimension table. So currently the most advanced solution to carry out multi-table joins. So bitmap join indexes deals with star join schematas. So you could call it bitmap star join index, I assume. And if a bitmap join index built on the attribute column of a certain relation, of a relation R, and the column S of another relation called S, and that is a bit matrix, a table B, which contain the index, with as many rows as the tuples of the relation R, and as many columns as a tuple of the relation S. So you will have one table as columns and one table as rows. So here we have an example. Tuple 4 in the fact table is joined to tuple of the dimension table, and tuple 2 of the dimension table is joined to tuple 2 and 4 in the fact table. And this takes less space and materialized views, of course. The picture here is taken from Golfarelli and Rizzi in their book Data Warehousing Design, Modern Principle and Methodologies. A really good book. So if you want to read more about data warehousing, I would deeply recommend the Data Warehouse Design book by Golfarelli and Rizzi. And it's available both in Italian and in English. So, we talked during the physical design video about partitioning, and that we can partition tables, and then so you can store the contents of a table in different disk blocks, or different disks for that matter, and different table spaces. And indexing can help you in this. So each partition would have an index of its own, of course. So if you want to search in an index in a table partition, you can use an index for that table partition. But of course there's also a global index. So you search a value, and then the index will help you, guide you to the correct data page in the correct table partition. And again, all the pictures are taken from a songbook from the early 14th century called Codex Manesse, which is stored digitally at the University of Heidelberg, and you can access it using http digi.ub.uni/heidelberg.de/ and so forth. Well, you have to look for it. Use Google or a search engine and search for Codex Manesse and University of Heidelberg, and I'm sure you will find it. Well, thank you for your attention, and please watch the next video in the series.